one end of the magnet is attached to a wire. But, and so the circuit could be, here's the magnet, has a little wire on the end. And here's the contact over here, and here's the circuit,
So,
okay? Now, right now, that circuit is open, right?
alright.
And if the solenoid is right around here,
Oh,
then the solenoid is gonna shove this out
and then it completes this.
and
Oh,
complete
okay.
the circuit, and that, then, so your air conditioner can.
So you're saying like the battery's on the whole time. It's
Right.
just not connected to the circuit.
But it's not gonna be working,
So-
it's connected to the power, but it's not gonna be working until you complete the circuit.
So does that mean it still uses the fuel, the energy from
No.
the battery? It just it
As long
stops.
as long as the circuit is open,
Okay.
there's no current coming.
Mhm.
And what'll happen is typically, thermostat, for example, is a little, bimetal strip, it's called, that bends when it cools, or bends when it gets hot, either one. And say it cools enough so that it pulls away from contact and breaks the circuit. And then as it heats up, it
Oh.
gradually unbends and finally makes the circuit, sets off the solenoid completes the big circuit,
Air conditioner.
and you've got the air conditioner going.
Cool. That's what happens with those these little things in school where like if you heat them up, the little, you know, the thermostats here, like
Yeah.
if you make them hot, it'll turn on the air.
Yeah,
So, after it like, the solenoid shoots the magnet through that way, does it like come right back?
no,
Like,
it makes the contact, and as long as the circuit is complete, the air conditioner is gonna stay on. So it has to stay there. But because the current in the solenoid keeps going, it keeps pushing on the magnet, and so nothing's gonna move. And then there's a little.
and so that's not taking power out of the battery?
No, not really. And then this probably has a spring here. Okay, and the spring gets stretched out, and then when the current goes off in the solenoid and the force is no longer pushing the magnet that way, the spring pulls it back and breaks the circuit.
So didn't you say there's no force on the inside of the solenoid? It's just a current.
Well, there's a magnetic
It's still
field on the
magnetic
inside,
force.
and so if that little rod is a magnet itself, depending on how you put it in there, it could be repelled
be.
by the magnetic field in the
And
solenoid.
what makes that solenoid get it charged? You just like, or like what part of the car is that? Like, are you just turning
Like
the
when
key?
you turn the key, it sends
when you turn the key, or when mine is keyless, you just push the button, it allows current from the battery to activate the solenoid, which then gets you into the starter motor, which is, and
So
that's.
it's kind of like a separate circuit, sort of.
Yeah,
To send the to the solenoid.
yeah, yes,
Can I go back? Can I go to the back?
yeah.
Okay, sorry.
The solenoid
Okay,
just
so-
makes the magnet.
See some other applications of this. Say we have a wire,
The solenoid is
say this is a wire, and there's a current in this wire toward the door. What's the direction of the magnetic field of this wire?
Is it a positive? Wait,
It's around it like that.
So you can't just say one direction, can you, if it's circular? And how about right up here above the wire?
That'd be,
It's toward you. How about here? Down. How about here?
Towards you.
Toward me, and over here,
up.
up. So what the direction of the magnetic field is depends on where you are. But say we have two wires. One of them's here. So big, long wire intersecting the blackboard right here, and one of them's right here. Also a long wire, also intersecting the blackboard. So what we're seeing is a cross section. Okay, and the current in both of them is in. Okay? So does this one have a magnetic field?
Yeah.
Pardon? Into the board, yeah.
What's the question?
What's the direction of the magnetic field of the left-hand wire?
And it's positive.
Clockwise.
It's gonna be clockwise around the wire, right?
The current's in.
Like that. What about that one?
Same thing.
Also clockwise around the wire. No, that's counterclockwise. Nope, that's clockwise. Okay, Now, let's call this number one and this number two. Number one has a field, right? Is number two in that field?
No, it has a field space.
You don't know, right?
It's not?
Yeah.
The field pretty much stretches out, right? It gets weaker as you get farther apart, but it's still there. So what's the direction of magnetic field of wire number one at wire number two? Now we've got a specific direction, up, down, sideways, whatever.
Down.
Why do you say down, Ross?
Because if you make concentric circles,
Yes,
the tangent at 2 of that circle would be down, like if you're
exactly.
going counterclockwise.
Or this one is over on the right side
Yeah.
of this one, so its magnetic field is down right there. Did everybody see that? Okay, now, and like this, what's the direction of the force on wire two because of the magnetic field of wire one?
Yeah, to the left.
Toward wire one.
Toward
Is he right? He's Ross, come on. He's right. And then you point your thumb in the direction of current, your fingers point in the direction of magnetic field, your palm is pushing in the direction of the force.
I'm understanding about the first one.
Yeah, how's the
What was
magnetic
the
field
tangent?
down?
What was that?
Okay,
It's like,
this wire is over on the right-hand side of this wire, right? Well, what's the direction of the magnetic field of this wire on the right? I mean, and just because it doesn't look like it goes that far, it does. So, it's,
Are you just like extending like a lot, like?
I'm just saying, like, if it were bigger, yeah. Okay, now what's the direction of wire number two's field over here at wire number one? It's gonna be up, right? Okay.
Which is gonna be,
So what's the direction of the force on wire number one from the magnetic field of wire number two? To the right. Like that, right? So those two wires are gonna attract one another. If they have current in them that goes in the same direction, they attract. What do you suppose would happen if they had current in them that went in opposite
They
directions?
repel.
They would repel, absolutely. Okay. And the force of attraction and repulsion depends on the strength of the currents in the wire and the distance between them and that kind of stuff. Okay, let's get another example. Okay, there's a circuit. Current in the circuit is away from the positive terminal of the battery. And part of the circuit, part of the wire is in a magnetic field. Is it gonna feel a force?
yeah,
yeah,
What direction?
to the, like,
it's going into the.
kind of weirdly, like,
What direction is the magnetic field? What do the little circles mean?
towards the board. Oh,
It
it's,
means
oh, it's
out of the
out.
board, positive Z,
So
right?
it's down, like down right, diagonal sort of,
Is there gonna be,
perpendicular to the,
It's gonna be down, like the bottom right corner.
I guess if we're looking at
like that?
yeah.
why isn't it, why is it?
Yeah.
Now, why is it going that way? The current is going that way,
Mhm.
right? Fingers have to come out of the board,
And it has to be at the same
the
angle.
field's out of the board. And so the
Oh.
wire, every proton in that wire that's moving that way is gonna feel a force pushing it down that way.
Why do we, know what the field and like towards us instead of
The
that
little
way?
circles.
Usually
And
X
usually
is
in diagrams will
the
say
way.
B, X is mean in, O is mean in. Okay? So there's gonna be a force on that wire pushing it down to the, and to a little bit to the right. And the amount of force, what do you suppose the amount of force depends on?
What's that the other
Formula.
one?
Yeah, they check
Depends
it.
on field strength, for sure, right? What else?
Velocity.
Well, but in a wire, we don't talk about the velocity, we talk about the number of coulombs that goes per second, right? Which is called the what? The current, yeah. And it makes sense because the more current there is, the more particles there are moving through the wire. And what else?
Mass.
Yeah, it
Charge,
doesn't, it turns out,
length.
the other thing isn't quite so obvious, but it's the length of the wire that's in the field. So if we made the field bigger, so it encompassed more of the wire, then that way. This is really easy to remember. All you have to remember is that force is Bill.
Bill.
Okay, so we have two equations for magnetic force. One is the force on a single particle that's moving, right? Remember what that one is? Stick with the same kind of thing. Let's say we have a positive particle. Well, let's think about it. Have a positive particle moving with the speed v going up in that direction. Tell me what that particle would do.
Feels.
It's gonna feel, it kind of like
It's
that.
force
The
that.
forces.
Initially, when it enters the field, it'll feel a force, like that, right? So what's it gonna do?
They're gonna start moving out.
It won't be in the field very long, will it? It's just gonna start to curve and it's gonna curve up and around clockwise until it leaves the field. Okay, and what's the amount of force on this particle?
The charge
Charge
is the field,
times the field,
times the perpendicular force.
in that case, what's the perpendicular velocity?
Because
Think about this, what's, the field is perpendicular to the board, right, coming out toward you? The velocity is in the plane of the board.
Oh, that's right. So
Geometrically,
it's already perpendicular.
It's already perpendicular, right? So it's the whole velocity that you use. If it weren't perpendicular, it would be going like this or something, and then you'd have to have information about the angle. Okay?
Wait, what exactly is your?
Are you ever gonna,
If the particle, the proton,